Lesson 7-2, Understand Theoretical Probability. In this lesson, we're going to learn how to determine the theoretical probability of an event. Take a look at the solve and discuss it. Betty and Carl will conduct an experiment. They will flip a coin 100 times and record the result of each flip. What should they expect the results of their experiment to be? Justify your answer. So let's think about what happens when we flip a coin. We know that there are two sides to a coin, which means we have two possible outcomes. And those two possible outcomes are heads or tails. So if I flip a coin 100 times, I should expect that the two possible outcomes happen in equal amounts. So about how many heads and tails should I get? Well, if I flip a coin 100 times, and because I have two equally likely outcomes, I should expect to get heads about 50 times and tails about 50 times to make a total of 100 flips. Now that's what should happen. So the theoretical probability tells me about what we expect to happen, and then if we actually conduct the experiment, that will tell me what actually did happen. Now, how did I get the fraction 1/2? Well, remember that each heads and tails should occur about 50 out of 100 times, which is equivalent to the fraction 1/2. Example 1. Use theoretical probability to make predictions. Talia and Yoshi design a game for the school fair. Contestants spin the pointer and win a prize if it lands on either of the two red sections. How can Talia and Yoshi determine how many people are likely to be winners if 500 people play their game? So let's take a look at the spinner and determine first how many sections are on the spinner and how many sections are winning sections. So step 1 says, determine the total number of possible outcomes. In this case, there are 16 sections and they are all the same size. So that means each section is equally likely to occur when you spin the spinner. Since there are two sections of each color, then the spinner has a 2 out of 16 chance of landing on any of those colors. Okay, looking at the spinner, each color appears twice in those 16 sections. Okay, and because it could land on any of the 16 sections, each of those is equally likely to happen. The theoretical probability, so here's your vocabulary word, tells us about what should happen. In other words, if I were to spin the spinner 16 times, I would expect that the red section would come up twice out of that 16 times. P, a capital P in this case, stands for the theoretical probability, what we expect to happen. The event is the outcome that we're looking for. So what you see here is an abbreviation that tells us what is the probability of spinning red. So the event is landing on red, and we're looking for how many of those outcomes are favorable. Okay, we have two red sections out of the total number of sections on the spinner, which is 16. So the theoretical probability that a contestant will spin red and win this game is 1 out of 8, which is the same as 12 5/10%. Remember, 1/8 is the same as 1 divided by 8, which is 125 thousandths in decimal form. And when you multiply that by 100, you get the 12 5/10%. So step 3 is to use proportional reasoning to predict the number of likely winners. So we can use that probability then to make another prediction. In this case, W is going to be the number of likely winners. If 500 people play the game, then that means I expect how many winners out of that 500? Well, I'm looking for what number divided by 500 is going to give me an equivalent fraction to the fraction 1/8. So we solve this proportion just like we did before. We've done this in previous lessons. Okay, this is a division equation. So we need to multiply both sides by the 500 in order to find W. So remember, W is going to be 500 times the numerator, 1, and then divide by 8. So W is 62 5/10, which means we expect about 62 or 63 people to be winners of that game out of 500. Now let's examine the triad. If Talia and Yoshi redesign their spinner to have 14 sections instead of 16 sections, would they likely have more or fewer winners? Explain why. Well, in this case, if we're looking at the same case of to win the game you have to spin on red, the probability of spinning red on this new spinner is equal to 2 sections that are red out of 14 sections now on the spinner instead of 16. So let's change that 2/14, or 2 out of 14, to a percentage so that we can compare it to the percentage that we had in example 1. So 2 divided by 14, do that first. And then take that answer, decimal, times 100. Now this decimal is a long repeating decimal actually, and you can't fit it all on the calculator screen, but what you can see is that when you multiply by 100, you get about 14 3/10%. So go back and compare that to the percentage that we had in example 1, which was 12 5/10%. If you have a greater percentage, then that means that you would have more winners of that game. Okay? The percentage is higher if you only have 14 sections rather than 16 sections. Example 2. Determine theoretical probability. Archie plays a word board game. He places 98 lettered tiles and 2 blank tiles in a bag. Players will draw tiles from the bag one at a time without looking. What is the probability that the first tile drawn will be a blank tile? What about the probability of a tile labeled with a letter? Or maybe a vowel or a consonant? So think of these tiles as being like the tiles from a game like Scrabble or Words with Friends. Remember that each of those tiles that you see appearing there, it has an equal probability of being selected from the bag. The tiles are all the same shape and all the same size. Drawing a blank tile means these 2 tiles down here at the bottom of the picture. There are only 2 of them out of the 100 tiles in the set. So that means there is a 1 in 50 chance, let me try that again. There is a 1 in 50 chance that the tile you draw first would be a blank tile. What about drawing a tile that has a letter on it? Well, if you look at that set of letters, there are 98 of them because 2 are blank. So 98 out of 100, or 49 out of 50, are your chances of drawing a tile with a letter on it. How about drawing a tile with a vowel? Well, in this case, you're going to have to go through and count up all the vowels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you look here, all these are vowels in the first 4 rows. I'm marking them all in blue here for a moment. And then there are 2 tiles in the 5th row. So how many tiles is that all together? 42 out of 100 or 21 out of 50. All we're doing is simplifying that fraction. And then what about tiles with consonants? All right, if 42 of them have vowels, then that means consonants would be the other 56 tiles. Now notice that we started with 100 tiles. 2 of them are blank. So when I subtract out 42, I actually get 58, but I got to take out the 2 blank ones. Okay, so if I don't want to count them up, I can use subtraction to get 56 out of 100, which is 28 out of 50 when you simplify it. So solving a problem like this, determining that theoretical probability, is nothing more than just ensuring that you count all the possible ways that that outcome can occur out of all the possible outcomes there are available. Now on example 3, you're really going to want to look at this one carefully. Okay, this is a very common problem that I see here that is used a lot. Okay, rolling a pair of number cubes. So in this problem, we are going to look at using the theoretical probability to make more predictions. Joaquin also designs a game for the school fair. Contestants roll 2 number cubes at the same time. If the sum of the numbers on the 2 cubes is 7, the player wins. Okay, so sum means we're going to add those 2 numbers together, and if the answer is 7, then that player is a winner. About how many winners should Joaquin expect if 500 contestants play his game? In order to make that prediction, the first thing that we need to know is how many different combinations are there of rolling those 2 number cubes, and what are those sums? So when you look at step 1 here, you're really making a chart that describes all the sums that you can get when you roll those 2 cubes. If you get a 1 on the first cube and a 1 on the second cube, you get a sum of 2, and so forth. And what you'll notice here is that the only way that you can get a 7 is by rolling a 1 and a 6, a 2 and a 5, 3 and 4, 4 and then 3, 5 and 2, or 6 and 1. So there are 6 ways to win the game, meaning getting a sum of 7 on those 2 number cube rolls. So how many possible sums are there on the whole thing? Well, in this case, there's 36. So there are 36 possible outcomes on this chart, or 36 different sums that you can get from rolling those 2 cubes. Step 2 is find the theoretical probability of rolling the sum of 7. So P stands for probability. The probability of getting that sum of 7 is 6 out of 36, or 1/6. Okay, simplify that fraction. Oops, now I'm not able to write. Let's try that again. Then we're going to use that proportional reasoning again to predict the number of winners. In this case, again, we'll call them W. So if we predict that 1 out of every 6 combinations or outcomes is a winning combination, I want to know how many people would that be out of those 500. So again, this is a division problem right here, W divided by 500. So we're going to solve that by multiplying 500 on both sides. Now remember, W is equal to 500 times 1, numerator and whole number get multiplied, divided by 6. That's how you multiply that whole number, 500, by the fraction 1/6. And when you do that, you end up getting a decimal that repeats. So we would say that Joaquin should expect about 83 winners. We need to round to the nearest person or whole number. In the try it that goes with example 3, Joaquin wants to reduce the number of winners so he does not have to prepare as many prizes. Choose another sum he could use as a winning sum and predict the number of winners if 500 people play his game. In this try it, you can pick any other sum from the table. So for example, if I don't want as many winners, I could say that in order to win the game, Joaquin would need to determine that the sum of, let's say, 4 is the winning sum. If that's the case, then the sum of 4 only appears 3 times in my chart. That still is out of 36 possible sums in the chart, which means the probability in a simplified fraction would be 1 out of 12. So if Joaquin has 500 contestants, how many would that be out of 500? So we're going to multiply both sides of that proportion by 500. And 500 times 1, and then divided by 12, leaves me with how many winners? In this case, there would be about 42 winners, because 500 times the fraction 1/12 equals approximately 41.6 repeating. So rounded would be 41.7, which is about 42 winners.